All right. Hi, everybody. We are continuing on to talk about creep. So this fits into the overall structure of the class very well because we've talked about plastic deformation way back early in the class, where we talked about the transition from elastic to plastic strains and how those plastic strains are usually much higher. But those plastic strains are expected to occur in a very short period of time because of mechanical loading to the component. Now we're talking about creep, which is a time and temperature and loading condition. And so it occurs over very slow periods of time. So there's some initial, let's call it instantaneous strains. And then as you wait over time, if it continues to have a heavy load and maybe be at an elevated temperature, then the material will continue to extend until it eventually ruptures, and it will subsequently, at the same time, experience degradation of properties. So we'll talk a little bit more about some basics today, and then I'll do one example. And I'm going to start with how do people try to measure things about creep, right, and try to quantify it such that they can do predictive design. This is something that is pretty standard as far as understanding creep. And this plot shows, it's figure 13.1 in the book, and it's the creep strain. So maybe epsilon creep versus time. And so you can see that there are three phases to this creep. So there's a transient creep, sort of happens more quickly right away. And then there's a steady state creep, which is what we usually try to quantify because it takes the longest amount of time and it tends to be described by an analytical equation pretty well. And then we have accelerating creep up here before there may in fact be a creep rupture. And so the rate of the creep accelerates. So that's the accelerating creep stage. The rate of creep slows down in the transient creep stage, stage 1, right? So it shoots up, but then the rate drops off, which would be the tangent or the instantaneous slope of that line. Then the instantaneous slope is pretty constant for a while, and then it turns upward. So that's the accelerating creep stage. So because it's a more complicated phenomenon involving time, stresses, and temperature, it's very hard to do testing at the conditions that you're trying to design for. Because it would take a very long time. And you would have to know the working temperatures or replicate some temperature spectrum applied. And so there are three ways that our book talks about measuring creep. And so I'm just going to go through them. And they all have sort of advantages and disadvantages. But I just want you to know that there's no perfect way to measure and predict then what creep behavior would be sometime in the future, or maybe at some other temperature or something like that. Okay. So the first method that our book provides, they just call it the abridged method. That's a very short name. I'm going to call it an isothermal creep test. And we talked a little bit about in the last lecture that there is a difference between a creep test and a stress relaxation test. A creep test is constant stress applied to the part, and then you measure some elongation, right? These are all done inside of a uniaxial tension tester. So then you measure some deflection over time. The part itself continues to deform and elongate. So that's what this abridged method is. It's a creep test, and it's done at you do it at all the same temperature. Okay? And then the goal of all of these methods is what stress can my part handle? Usually, this is what we're solving for because we can't control the creep strain at which these things eventually break, right? That's a material consideration. It is what it is. There's a creep rupture strain. That's the maximum we can have. And then we also usually need to design for a design life, right? I need it to last X amount of cycles. So these are either system configurations or material considerations that are unchanged. But a lot of times we can reconfigure something, change the loading, add in another gear, whatever it might be, to change the stresses on a particular location. Remove stress concentrations by having smoother transition between parts. There are all kinds of things you can do. So that's why these methods are used for predicting what stress I can use in design. Okay, so I'm going to go to the next slide and draw this plot. So here's the abridged method. And so we are going to make a plot of the creep strain versus duration. So I'm just going to call this sigma or epsilon creep, CR, and a test duration. And then we're going to have these be isothermal. So same temperature for all of them. And then what we're going to do is apply different levels of stress to the part. So if we apply a really high level of stress to the part, right, we might actually get a stress rupture. We don't want that because we lose a lot of our steady creep zone, right? And so if we drop the stress level a little bit, then we start to get some more out in here like this, these longer regions. So I'm just going to draw them like this. And they kind of flatten out a little bit more. You go lower in stress, you get lower creep strain. So these would be different stress levels. And in the book, they call them like S1, S2, S3. And you actually measure it out to some test duration. And you don't have infinity time in the lab, so usually this is some number of hours. Could be one day, could be a few days, could be a few weeks, depending on how well you need to know this. So that's the data that you get from the experiment. Well, unfortunately, design life is usually past that, 1,000 hours, 10,000 hours, whatever it might be. So what we actually need to know is what happens out here at our design life. And so the only thing that we really can do is if we know this, how the behavior is in that linear region, we could just extrapolate it out. And so that's what's done. It's just you say, okay, I'm going to go out to here and just extend these lines out to my design life. Right? And so there are some limitations to this, as you can tell. So that's one. So we have to get somewhere out on that vertical line. We have to be on that design life. And the other thing we have is we know there's some maximum of creep strain that we can get for the design, right? So maybe there was like a safety factor or some limiting design strain based on performance, because as things change dimension, all of your dimensioning and tolerancing changes if this part is interacting with other parts. So there's going to be a limiting design strain right here. So I'm just going to call that like epsilon D. And so what we do is we say if that's our limiting design strain, right, we can just draw it over here and find the intersection point of the design life and the maximum design strain. And then we can kind of say, okay, I have these other stress levels in there, but I didn't have that exact point, right? But you don't need that exact point. You can sort of say that you would expect that the stress would have the same sort of trend like this, right? And you could predict what it would be at some sort of interpolated slope between those two. So that's how you get your design stress from that kind of an experiment. Unfortunately, you cannot really figure out what's going on with these kind of tests without doing this entire suite of testing at multiple temperature levels, right? So this is isothermal. It's a standard creep test. We're just extrapolating out in time, putting some hard constraints on it and saying, okay, what's our maximum stress we should use in order to not exceed those things for this particular application. So that's the abridged method. The next one is called the mechanical acceleration method. So I'm just going to call it number 2, mechanical acceleration, and that is what it sounds like. We have a much increase in the stress levels that are applied in the experiment. And so if we have stress levels that are kind of an input to the experiment, then what happens is this is actually not a pure creep test. So we put a stress level in, but what we really do is control the strain. So this is actually a stress relaxation experiment. And they don't really talk about that too much in the textbook about why they allow these two sort of complementary methods to measure the same thing. But this is what they're presenting to us. So this one is, I'm going to call it an isothermal stress relaxation experiment. But the goal is still the same. What stress can be handled? Okay, and so this is plotted a little bit differently, but it's similar as far as like taking data, extrapolating out, putting on constraints, looking at what you get. So I'll draw that on the next slide here. So in this case, if it's a stress relaxation experiment, we're going to be plotting, instead of a strain, creep strain on the y-axis, we're going to be plotting a stress level. And on the x-axis is still the duration in hours. Okay. And they call this mechanical acceleration, and they say that it's done at increased stress levels, but really it's done at increased strain levels. As I said, it's a stress relaxation experiment. So the first thing you do is crank this thing up to just really high strains. Right? And so you crank it up to a really high strain and then just leave it there. But you don't change the deformation. Okay, so whatever you put it at, you hold that distance constant in the experiment. So you start at some really high level of stress, and then eventually that stress will fall off over time as the stress relaxes out to some test duration. So this is our lab test here. We can only go X amount of hours in the lab before we have to move to the next sample or whatever. And then we do it again, and we move to a slightly lower level of strain. And then it drops off like this, and then we do the same thing again, and we sort of have something like this. And so they call this, in the book, they call this like a design, they just call this like a strain level. So we have like delta 1, delta 2, delta 3, but these don't mean some kind of principal strains or deformations. These are just different levels that they've started the test at. So that's what we get. And if we fit this to some kind of a decreasing function, then we can extrapolate out to our design life, thousands of hours. Right. So we just sort of keep drawing the lines like this. Right. And then in this case, we look at the design life, and we look at sort of what our allowable strain is So let's say that this middle strain is our design strain. That's what we expect to be kind of the maximum. So we take that delta 2 and we follow that down to this design life. And what that tells us is the stress level, based on this plot, way back here, right? So that becomes our design stress, because that will be the maximum that we should use in order to have our design strain have that maximum and be able to hold that stress at the design life. So it's slightly different, sort of flipped method. And then the third one is a thermal acceleration method, in which case they crank up the temperature and then try to come up with a stress from this. Give me 1 second. I wrote down that this is also a stress relaxation test. Yes, it must be. Okay. And so this is not an isothermal experiment, but rather the temperature is changing. And it's at high, like super elevated temperatures, but still we want to get out what is our design stress. Okay. So we're going to plot something similar to what we plotted before with the different levels of input strain, but plotting the stress and time or duration on the x-axis. And instead of having like a drop-off with sort of a concave downward of the strain, now we're plotting for different temperatures. And so we bring up the design stress for a constant strain. So in this case, I'm going to write strain equals constant. We're not changing that at all. So it is a stress relaxation experiment at different levels of, or at different temperatures, same strain. All right. So we take that and we make just sort of plots like this out to our testing lifetime here. And so this would be for a lower temperature. And then as you go, is that right? No, I think that would be the higher temperature, right? It does not specify in the text. We're left to our own devices. So I think that's higher temperature, and I think this is lower temperature. And so that's what we have. And so these are more like straight lines than curves, so maybe easier to extrapolate out to our design life. And so these curves go straight out like this. I've kind of drawn them a little bit funny here. But then we look at where our design life hits our operating temperature. So we do a whole suite of temperatures, and then we say, oh, I think my situation is going to operate at kind of this temperature, and then I can take that over and get the allowable stress. So this is a way of doing experiments on particular materials that might be used for design, right? This is not, we don't have equations coming out. This is not predictive. This is just how the measurements were taken and then how they're plotted and what can be done to sort of use plots directly. Okay. And so many of these experiments were done, and as researchers do, they tried to come up with ways of quantifying the trends that they saw, right? So the first model that the book tells us about is called the Larson-Miller parameter. All right, so Larson-Miller parameter. And the reason that it's not called a model is that we don't have a particular model for this, but we know a few things are important. We know temperature is important. We know time is important. And we also know that stress and strain are important, but we have a lot of relationships already for stress and strain. And so the first researchers said, we can handle stress and strain. What we can't handle is this temperature and time. So what we need is something to handle that. So then they decided to come up with parameters. And you could think about this as kind of like a state variable. Like this describes a particular combination of time and temperature. And then if you match that parameter at a different temperature, you could adjust the time to compensate, and you would still get an allowable situation. Right? So this parameter is written like this. It's just given the capital letter P in this text. And so we have temperature is given by the variable theta here. So I'm going to use their terminology. We have theta plus 460. That quantity times the quantity. Some constant plus the log of time. So P is the parameter, theta is the temperature, and in this case they have it in degrees Fahrenheit. C is a constant, they said usually assumed to be 20, and then T is time in hours to reach a particular value of creep strain. So hours to some value of creep strain that they would define. So you'll notice here that this parameter is a function of the log 10 of time. Okay. And so what they say is, okay, if I'm going to change the temperature here, and I know what this parameter is for a stable system, then I can change my time to compensate. So if I have to go to a higher temperature, I can do that for a lower amount of time. But if I can operate at a lower temperature, then I have a longer period of time. So the general idea here is time temperature superposition, where we're combining those two effects into some kind of a parameter described mathematically by these researchers like this. Right. So that's one model that's given. The next model that's given has a similar idea, but the form of the function is just different. So I'm going to go to the next slide to make sure I can write it all. It's not long, don't worry. So this one is called the Manson-Hayford parameter. And you'll recognize Manson as being one of the researchers we've referred to a lot in talking about cumulative damage. So they had a parameter, we'll call it P prime, as not to confuse it with the other one. And in the numerator, we have temperature, theta minus some constant related to temperature. And then we have log 10 of time. Minus a constant that's basically very similar. So we'll have theta A and TA as our material constants. Similar as before, theta is in Fahrenheit, time is in hours, and then this theta A and TA are constants, material constants. Okay. And it says in our textbook that these have been shown to fit well to a variety of materials, right? So different types of metals, but also some plastics and some ceramics. So they are general parameters you can use. There are no no problems at the end of the chapter that include these parameters because I think they want they want us to use more fundamental analysis, but I wanted to present them to you to show you that there are a variety of ways to go about this. We could probably find 3 more journal papers with 3 different functional forms. And those can be good for very specific design problems for which these have already been shown to fit well. But we're going to talk about this a little bit more generally, and because what we really want is not this kind of parameter and then to try to have to handle stress and strain differently, but we want to be able to add in this to our understanding of stresses and strains already, and maybe add on a creep strain on top of an elastic strain or a plastic strain or whatever, so that we can solve problems and say, I predict that this sample is going to elongate that much in the next 1,000 hours, which will meet or not meet some design spec. I wanted to show you a plot from the textbook, which is here, and it's figure 13.5, and it gives just a wide variety of stress versus temperature regimes. So it says short time creep tests for several materials, showing curves of stress versus temperature for 3% total deformation in 10 minutes. Okay, so on the left side is these low temperatures. So I'm just going to write low temperatures, and by low I mean like room temperature. And then elevated temperatures are to the right side. And so these are for stress versus temperature in 3% total deformation in 10 minutes. So the left side of these regimes is how much, if it's at a constant temperature, how much the stress is dropping in 10 minutes. And then they stop it when they get to 3% total deformation. So you can see that the stress, if this y-axis goes from 0 up to 100 here, and it's in thousands of psi, so this is essentially KSI, then this material with these hatch marks, where I've kind of drawn this arrow, right, drops from an initial stress in the experiment, it looks like about 88 KSI, down to like, I don't know, 32 KSI in 10 minutes, right? So that's a significant drop. So these would be like stress relaxation experiments. So something is relaxing inside that material because of the constant load, elevated temperature, and some time in order to give that drop in the stress. You can see that these curves have a lot of different slopes, and they're kind of regions, right, that characterize different materials. It looks a little bit like an Ashby plot. Okay? So this is really why we need some sort of systematic way of dealing with this. Right? We need to do something to collapse this x-axis in temperature, right, because there's so much span there from 200 Fahrenheit up to like 2,000 Fahrenheit. And so we really need a systematic way of dealing with this. The book gives us a nice idea of more motivation, why we need to study this. And so if you have a uniaxial creep test, right, and you have like your little section in the middle that's reduced in diameter so that that's what you're measuring, you put this in here. Okay. With increasing temperature, there are a variety of other factors that are changing simultaneously. So if we have increasing temperature, like we saw sort of going to the right on that other diagram, right, the ultimate strength of the material drops. So, okay, we know there are some ramifications on that. We use the ultimate strength of materials usually as a basis for its ability to resist fatigue. Right, our rule of thumb for what's the endurance limit of steel is half the ultimate strength. Well, if the ultimate strength goes down with temperature, our ability to resist fatigue goes down. Okay. In addition to that, the yield stress often drops. Right? And this is all with increasing temperature. So the yield strength decreases. We know that we also will have a change in any kind of other like yield criterion and some things related to cracking and fracture, right? So elasticity, fracture, and low cycle fatigue. because a low cycle fatigue assumes that at some point, if the stress is low enough, we'll have most of the elastic deformation. At the same time, we get the sample is elongating, right? So we're building up really high strains. And because of these other things that are happening, stress concentrations usually are not as high because everything is having a little bit of relaxation locally. So you have stress concentrations going down. So these are kind of like competing effects, right? If stress concentrations are going down, awesome. But at the same time, our ability to withstand that stress is going down, right? Our yield strength is also going down. So unfortunately, we are going to have to use this sort of uniaxial test data in order to interpret things. But we need to somehow at least have these trends in mind because they'll inform some of the ways that we interpret the data at a later time point. So here's going to be the basis of how we approach this analytically. Okay? So we're going to look at experimental data from different types of materials. And on the x-axis here is time. This is, I think, figure 13.6 in the book. And it's bigger, but I sort of cropped it off so that we could see the axes. So we have time on the x-axis in hours. It goes from 0.1, so it's on a log scale, to 1 hour, which is right here, all the way up to 1,000 hours. Okay, so that's a pretty long time. And on the y-axis is creep in inch per inch. So this is going to be the sort of, actually it's not epsilon. This is going to be, I think, the delta. So it's the elongation, right? No, it's inch per inch. Hang on. No, it's okay. It is the strain. Let me go back, put that off. I can look at the units. Okay. That's unfortunate. Okay. Give me 1 second here. We're having some. Okay. Strain. Okay. Pen. Okay. There we go. So it's our epsilon in inch per inch. At the top is, okay, so ignore this value here and this value. Okay, so ignore that value on the bottom there. So this is 0.1% up here at the top for scale A. So on the left side is 0.1%, and that applies to this high purity aluminum wire. Just kind of highlight that here. So that's one material. And then they want to give us all this information on one plot. So they put a different scale on the right side, and that's for figure B, which is medium hard drawn copper wire. And the 0.001 is right here. Okay? So what we can sort of understand from this initially is that if we have aluminum wire and we wait 1,000 hours, it almost reaches or barely reaches to 0.1%. If we have a copper wire and we do the same conditions, we get that it goes, for this one anyway, it goes above 0.1%. And that makes sense with our intuition, right? Copper is known for being really, really ductile, creeping really badly, so it should have these higher creep strains compared to something like aluminum. Okay, so that makes sense. These lines on this plot show us that there is on a log-log scale, there can be a linear relationship that describes these things. So we can write it like this, right? Delta is the true creep strain, and that's going to be some coefficient times time to some power, right? So this is like just general form, right? We have a coat with the little a and the big A are just empirical constants. T is time, and so we can write that based on this data. Okay, so that's one thing that's helpful. But another thing that we care about is the rate of creep. Right, so if we can describe the rate of creep, at least qualitatively at first, then we can apply it sort of quantitatively and put it back into some of our strain rate equations that we had before, and we can do some manipulation there. So if we differentiate that with respect to time, then we get, just the coefficient, the power coefficient out front now, little a times big A, to time, and then we subtract 1 off of that exponent, right, a minus 1. So all we did was differentiate. And then we can generalize this, and so we don't have to have a times a, so we can just say that delta dot is equal to some constant, let's call it lowercase b, times t to the minus n power, because the strain rate decreases the more you go up. If we plot this on a linear scale, it would have sort of a concave downward trend. And so that's why we have that exponent like that. Okay, so this is kind of going to be our guiding equation. I'm going to write it on the next page, and it's going to help us categorize the rates of creep rates. So delta dot is equal to b times time to the minus n power. So we can identify a few different regimes here. So we'll categorize them by n, and we'll give that some name. I'm going to call it creep type. And then we'll have some equation to describe it. If we go and then sort of reintegrate that, and then what it applies to, what types of situations. Okay, so this is not in the textbook, but they describe it like this in the textbook, so I went ahead and made a chart. So if we have, we'll start with sort of the easiest one. So if that n is equal to 0, then our creep rate is actually constant. So it's a constant rate creep. Because if we put 0 in there as the exponent, that means t to the 0, that's 1. So we just have delta dot equals b. The creep rate is a constant. And then if we reintegrate that with simpler variables, all we get is the creep strain, what they're calling it delta, is equal to some coefficient b1, they call it b1 times t, plus maybe some constant of integration. Right? So we just made the exponent 0 and then reintegrated, so now we just have the strain. It's not a rate anymore, it's the strain is just a constant times time. Okay? So this applies to materials at very high temperatures. So once you go high enough, the materials don't deal with stress very well at all, and then the rate of creep is just a constant. It's no longer affected by other types of things, like material properties and stuff. At another point on this spectrum, we could say, okay, what if n is equal to unity? This is called logarithmic creep. And if we integrate that, then we have b times t to the minus 1. And so we get the creep is equal to, let's call it b2 times the log of t plus a constant of integration. And this is good for a lot of different classes of materials. Gives in the book, it says everything from rubber to glass to lower temperature metals. So it applies to tons of things. So you will see now that you can apply this directly, right? This harkens back to those parameters that we talked about at the beginning, where people were trying to relate some state variable, some parameter, to the time and the temperature, And in this case, in that case, they had, one of them was a logarithmic rule. Here we find the log again. And then what if this is some value in between 0 and 1? Well, in that case, it's parabolic creep. Right? And then we have some power that we can't get rid of there. Right? And so the form of the equation is like delta equals some constant times time to an exponent. They call it m. I don't know why they have so many different variables in the book, but there we go, constant of integration. And this can be good for intermediate and high temperatures. Okay. And so this is just kind of an exercise of general sort of creep rates. We can bin them into these different types if we want to choose the simplest one that we need for the application we're looking at. Okay, so this is good, except we're only with time now. We don't have temperature anywhere. So this isn't quite as helpful yet. And they say in the book that B3, so that's the last constant down there in our description, so B3 increases with stress and temperature. And then M decreases with stress, but increases with temperature. So we still need different constants that describe all of these different situations, right? But if you know the material and you have access to testing equipment on that particular alloy, then go for it, right? You can put it into one of these bins. You have all of these constants that you fit from the data, and then you can do a good design. Okay. So we need to somehow incorporate now stress into this. Okay. And I'm unhappy with the textbook right here, but we're just going to go with it for now. So they say the influence of the stress level or creep rate, and creep rate can often be represented by an empirical expression. And then they just throw it at us. They say the creep rate is equal to some constant times stress to some power, right? So to me, I wish they would give us a little bit more of a background on why this is the case. Maybe just based on the testing that they had before, different stress levels. And recall, we already had defined maybe a rate as being some constant times time to the minus n, right? So you can sort of see there's going to be a way to combine these together. We are going to assume that stress is independent of time. So stress is not some function of time. Okay. But those are independent. We have a stress level, and then we have some time, we have some duration. Okay. So we can integrate this with respect to time. And all it does, because time is not in there, is it just adds a t, right? So we get delta dot is equal to some constant times time times stress to some exponent n, and then we'll keep our little constant of integration there. But the constant of integration is usually very small, and so it says that we kind of just assume it's 0. And so this is called the, if we sort of circle this right here, the log stress time creep law. There we go. I think they need to replace the batteries in the chime there. It's been, the tone has been dropping in frequency like every class slightly, and now, yeah, it's almost gone. Okay. And so this is described in the book as the log stress time creep law. It's equation 1311. and it's described as useful as a design tool. Okay, so I'm going to just set up an example problem that makes use of this as a design tool and sort of just manipulates this equation a little bit. Hang on a second. Did I write that wrong? I did. That should not be delta dot. That should just be delta. Let me go back. Okay. We integrated with respect to time, so it's not a rate anymore. It is a magnitude. Okay, so that's correct now. And so we can change that equation around a little bit. And so we can solve for what is our stress, right? So in all of the measurements that people do sort of to come up with these things empirically, they're always thinking about what is my allowable stress, right? So we can reconfigure this and we can say that our allowable stress, right, which might be some failure stress, is equal to the quantity delta divided by the constant times time, right, to 1 over that power that we had before. Okay, and so that we're going to use that setup. So the problem is, I'll draw it on the next slide. It says, suppose, for example, that it's desired to design a solid circular tension member 5 feet long. Okay, 10,000. It doesn't say, okay, it doesn't say the diameter, so I'm just going to assume it's some kind of rod like that. It's 5 feet long. Made of 1030 steel. To support a 10,000 pound load, we're going to assume that's tension. So put it as P equals 10,000 pounds for 10 years. So our time, or our duration, is 10 years at 750 F. 750 degrees Fahrenheit, without exceeding 0.1 inch creep deformation. Okay, so our allowable creep deformation is going to be 0.1 inches. And it is desired to incorporate a safety factor of 1.25. All right, so this could be a strut in a bridge or some sort of support component, right, that has to be under a load for 10 years at a high temperature. Right, so maybe it's in a factory or a foundry. Who knows? Okay, so what we need to do is find out actually what diameter this thing should be. So find diameter to withstand creep. And we are given that the constants at this temperature, so I'm just going to write it like this, B750 for this steel is equal to, these are crazy numbers, 48 times 10 to the minus 38th power. And capital N, that exponent that we need, is equal to 6.9. Okay. So we will use that, and we'll calculate and see if we come up with anything reasonable based on those kind of numbers. So I'm going to end this lecture here. We'll have like a 5-minute break, and then we'll pick it back up in the next one.